Thanks for coming back. So I'm going to give the second of the lectures on speech. So this one is mostly going to be about text-to-speech, speech synthesis, but I'm just going to finish off the last couple of slides that I saved from Tuesday about speech recognition. So we talked about speech recognition from acoustic features, but there's increasing interest in training systems end-to-end. So basically we would like to go from whatever raw signal we receive and ultimately output the kind of output that we really want, which is typically characters or words in the language of our choice. Possibly ideally formatted with capitalization and punctuation, which currently is done in a separate process. So there's been this push to train systems end-to-end with the idea that if you build a complete system end-to-end, you can optimize every part of the system with the metrics that you really care about. And so some of that has been some of that effort has been pushed into outputting characters and words instead of outputting phonetic symbols, the phonemes, with the idea that a single network or the complete system will learn the pronunciation model rather than us training a separate pronunciation model, optimized separately with a different set of metrics. So we saw some of those models outputting characters before. On the other end of the system is trying to simplify the feature computation. So we started with these hand-curated, human-designed features like MFCCs, which are designed to dimensionality reduce the waveform that we got. But basically, the waveform is what we get originally, and if potentially we can optimize the feature processing by operating directly on the raw waveform. So instead of working on the reduced dimensionality signal like MFCCs or log-mel, can we learn to process the raw waveform? And most people think about that in terms of learning filter banks. So the filter banks are you can think of an FFT as basically you're convolving a sine wave with the signal. But instead of having a sine wave, maybe we could learn something else that wasn't sensitive to just a single frequency, but learned the kinds of patterns that are actually in speech. And there's been several efforts at doing this. One problem with doing it is that if you're running an RNN, the dependencies now become very long range. We're processing 16,000 samples a second instead of 100 frames a second. So the dependencies become very long range. So just running an RNN on the audio it's a lot of computation, and it means long range dependencies to learn. So just simply doing that probably isn't going to work. So a number of other approaches have been tried. One is just putting a convolutional filter on the front end of an existing neural network system. So one effort has been to put a convolutional filter on the front of the CLDNN architecture that we looked at before, and I'll talk about that in the next slide. Or there's the WaveNet style architecture, which we'll come to later for TTS, which has also been applied for speech recognition, although only a sort of very rudimentary speech recognition so far. Another possibility is something like the clockwork RNN, which was basically running a hierarchical RNN where you have one RNN running at sample frequency, but then you successively downsample in time. So you have a higher level RNN that runs at half that rate, and another one running at half that rate, and another one at half that rate. And eventually, the top level RNN is processing at a more manageable frequency and can learn longer range dependencies. The original clockwork RNN paper was applied just to memorizing signals, but you could conceive of applying it to speech recognition. So one thing that was done was just learning these filter banks. So in the CLDNN architecture, we just add a convolutional layer on the waveform instead of using log-mel filter banks at the first level. So maybe we would learn 128 filters. And basically the parameters that we're learning are the weights of a convolution that's going to be applied to the raw signal. So if we could initialize them, say, with a sine wave, and we'd learn things that were similar to FFTs, or we'd initialize with something similar to FFTs. This is an experiment that was done with the CLDNN. the blue dashed line shows the log mel filter banks that we would use if we hand designed. If we chose 128 of those and just indexed them, you see the frequency on the left-hand side. In this case, if we initialized with just random weights in these convolutions, where we apply a convolution, I think in this experiment we took 25 millisecond filters and convolved them over a 35 millisecond window and did a max pooling at that point. So we are basically throwing away any phase information and just taking a magnitude by finding the maximum response within that window. Here we trained 128 filters, and they're going to be just sort of randomly assigned which filter does which thing, but after training you can find the maximum frequency response and then sort by that frequency. So that's what we've done here. So now the index is after this sorting, and we can look at those frequency responses. They're not going to have such a pure response as the log mel filter banks. They're going to respond to multiple frequencies, but we see that they're shifted so that we've got more filters looking at the low frequencies and fewer filters looking at the high frequencies in this case. So we've learned something different to what we hand initialized. And this is very much dependent on the kind of data that we use. So we see different behavior if we train on noisy data versus training on clean speech. And also we can initialize, in this case, we initialize with gamma tones, which are these sort of wavelet filters, where it's basically a sine wave modulated by a Gaussian envelope. We could initialize with filters hand designed, but then learn, and we see similar filters. So one thing that I just wanted to cover briefly is speech recognition in noise. That's become an increasing focus as we got better at doing speech recognition in clean speech. Then the emphasis is to try and extend that performance to noisy data. And the most general approach that seems to work very well is just to use noisy data in training. So you're matching your training set to the test conditions that you care about. And you could just collect noisy data, but a more general approach is to collect fairly clean data and then add synthetic noise, add noise synthetically when you're training. So I can take a clean utterance and then corrupt it with some noise that matches the kind of conditions that I'm going to experience at test time. At Google, we did this. I mean, you can do it simply by just adding a signal. You take a noise signal. We actually took a lot of our noise by taking non-speech segments of YouTube videos. So it's got a mix of music and other sound effects. So you can just literally add that to the signal. And you want to control for the signal to noise ratio. So again, you're matching the kinds of conditions that you're going to see in test. But you can also add that signal via a room simulator, where you're basically doing a 3D simulation of what it would be like if you had a noise source emitting that sound, a speaker emitting the speech signal, and then a microphone or multiple microphones at different locations in that room. And you can control the characteristics of the room, the distances and of the microphone from each of the sound sources. You can add multiple sound sources and so on. So this becomes much more general. And in particular, it adds reverberation. Now, in practice, we do this with real signals in the Google system. The actual speech signals that we've got are real recordings. So they're actually already being corrupted by the channel of recording them over a phone, being recorded in an original environment with noise and reverberation there. But we corrupt them further by this adding the noise to generate more difficult signals that the neural network can learn to basically be invariant to the noise that we've added. Because the labels, we still know the exact alignment between the labels and the clean speech. Another approach is just to train a denoiser, where you put noisy speech in and train it to predict the clean speech. Again, you do this by taking a clean signal, adding noise to it, so you now have the original clean signal and the noise corrupted signal, and you can just basically you're training a denoising autoencoder by feeding a noisy signal and asking it to predict clean speech. But again, an end-to-end system. If you want to do speech recognition, it makes sense to do an end-to-end system where you feed in noisy speech and you train with the objective that you care about at the end, rather than decoupling it into two separate systems that you're training separately. Although you can also add a clean speech reconstruction loss and do multitask learning, so you can be training to recognize speech, but have a secondary loss where you're actually checking that you can reconstruct the clean speech. And that even allows you to use unsupervised data, where you use data for which you don't have transcriptions to do where you're only using the reconstruction loss, and then for where you do have a transcription, then you actually use the speech recognition loss as well. And something I mentioned before on Tuesday, I think, is that if we're actually speaking in a noisy environment, then our voices change. So just adding this synthetic noise isn't really a true model of the situation. The Baidu team, they collected data in Lombard conditions, but I think they've not used that so much. I think that in fact, you get most of the benefit from just adding the synthetic noise. Now, final topic for speech recognition is something that's, again, becoming more interesting as we've got good at doing single microphone speech recognition. How can we exploit multiple microphones? I mean, it's long been a topic of research, but it's becoming more interesting as we get consumer devices with multiple microphones in. Before, it was the domain of sort of very expensive meeting recording rooms where you paid for a lot of expensive hardware. But now, even a mobile phone has at least 3 microphones in general, and is already doing some kind of denoising for the telephony. Can we use those microphones in the devices for improving all acoustic processing? And we also now have these devices like Amazon Echo and Google Home, where we've got these devices in our homes with multiple microphones. How do you exploit that to get better recognition? And basically, just simply having more microphones is clearly going to give you a richer representation of what's going on. If you can space the microphones out like you might have in a meeting room, then just simply picking the microphone where the speech appears to be loudest is going to help you. It's going to be the microphone closest to the speaker. But can we combine them in interesting ways to get even better performance? And a well-established technique for this is beamforming. If you know the geometry of the microphones, then if you can work out where the speaker is, so I say there's a noise coming from over there, then from the geometry I can work out how much longer it's going to take that sound signal to reach each of my microphones. And then just by delaying the signals to line them all up and then summing, then basically I get constructive interference of the signal that I care about, and I'll tend to get destructive interference of any other signals. And there are all kinds of refinements of beamforming about what kind of criterion you're trying to optimize. Am I trying to track a speaker? Am I trying to remove a particular noise source, and so on? And what kind of loss am I optimizing? But now we've got these neural networks where we can feed in high-dimensional information, then maybe we can work out ways to feed in that signal into the neural network and allow the neural network to do this. So one variant of that has been this work from 2016, which is the factored multi-channel raw waveform. So this, again, is a raw waveform version of the CLDNN, but where we take in this case, 2 signals and apply filter banks to each of those 2 signals and combine them before doing doing a time convolution. We do the pooling and then feed that into the frequency convolution front end, and then we have this LSTM and the DNN for the output targets, and a multitask objective for reconstructing clean features. And some of the sort of things that you can look at with the filters, you can look at, these are the impulse responses of some of the learned filters. And you can look at the beam pattern of these paired filters when you're looking at how they behave when you've got a joint filter looking at 2 different microphones. You can look at the angle of arrival, in this case, relative to the microphones, and the frequency, and see the frequency response at each of these angles of arrival. So you're tuning to get particular directions of speaker, and consequently also this is done per frequency band as well. So depending on which direction you get, you're going to get this constructive interference or destructive interference for different frequencies. We're learning these filters according to the data set. And in this case, it was a data set where the speaker location was randomized in this virtual room. Okay, so the slides will be online. They have all the references in. So I can quickly pause and see if there are any questions here. Okay, feel free to ask questions as we go along. So now I'm going to talk about text-to-speech synthesis. This is not the area that I've worked in directly. I've worked with the text-to-speech team at Google over the last few years, but it's not really my specialist subject. So I'm going to talk about the different kinds of text-to-speech, and then focus on the sort of neural network approaches to text-to-speech. And these slides are from my colleague Hager Zen, who has spent his entire career working on text-to-speech, originally with hidden Markov models and Gaussian mixture models, and more recently he's done a lot of the original work in applying neural networks to speech recognition. So again, now the task, instead of recognizing from a waveform to text, is to go from text to a waveform, which we want to be recognizable and usable by humans. So a little bit more detail than we had on Tuesday about the speech production process. So here the idea is that basically we have thought processes that lead us to some text that we wish to speech, some discrete linguistic representation that we want to turn into audio. And the way we do that is we modulate parts of the vocal tract. So we've got the vocal cords generating the fundamental frequency, and then we've got the resonant cavity that we can change the shape of to change what resonances we have, and to control the volume and give things like fricatives when we close the lips, and so on. And we can model this, so there are sort of fundamental parts of this that we can model. So people have spent a lot of time, like they're actually sort of X-ray movies of people with sensors on their vocal tracts and on their articulators. So people have actually modeled the trajectories of the articulator. So where do you put your teeth and your lips and your tongue? How fast is the vocal tracts opening and closing, the vocal cords opening and closing? So you can actually have a laryngograph that measures the resistance across your throat as well, that can see the opening and closing of the vocal cords. And we can characterize the speech production process in a number of ways. So one of these is the articulator motions, and that could provide a low-dimensional representation for speech, and people have tried to model speech in that space. It's very hard to get that data. I mean, nobody now wants to have X-ray movies taken of them. So we have very small data sets for that kind of thing. But say a laryngograph can give you these opening and closing of the vocal cords. We can model the fundamental frequency, which is the sort of dominant lowest frequency during the signal. And modeling the frequency transfer characteristics. In fact, some of the earliest speech synthesis attempts were with physical models, where you've actually got a series of pipes that you're opening and closing, and the resonances of those pipes you combine to make speech-like sounds. So if we want to do speech synthesis, we're starting from this text representation, and we want to get to the acoustic representation. There's a lot of processing in the text domain that we might need to do, depending on how we generate that text. Typically, we have a text which may be a complete document. Say we want to read an audio book or a newspaper article. We need to segment that into sentences, segment the sentences into words, which depending on the language may be trivial or non-trivial. text normalization to work out what the pronounced form is. So if I've got 1000, then that's pronounced in some cases as 1000, but in other cases we may actually pronounce it as 1000. Or we may even say, 1800 is 1800 or 1800. We need to know what the words that will be said are, and that very much depends on the context. So if I'm just reading some text about 429 people, the number 429 is 429. But if I'm getting driving directions and I say the A429, then I wouldn't say the A429, although Google does that at the moment. No. So there's a lot of text normalization to get text into the correct form that we want to be read, and a lot of that is ambiguous. It started out being done by rules. Increasingly, it's done by probabilistic models, and now neural networks, RNNs, and so on, to find the maximum likelihood representation that we should use. And we also need to get to the pronunciation. So from the text form, after we've worked out the spoken text form, we now need to turn that into a sequence of phonemes. And some of those things are ambiguous. We've got words that are written the same but pronounced differently. And things like place names can be pronounced differently depending on which place you're referring to. So we have to work out what the pronunciation that we want is for that written form, even after we've got that from the document. So all of that is sort of in the discrete domain. It's the domain of natural language processing. It's called text normalization as the front end for text-to-speech. Then, given that phonetic representation, then we have to turn it into a waveform somehow. And that goes from the discrete domain to the continuous domain. And that's really the focus of the text-to-speech problem. So there have been a series of approaches. The earliest were the sort of rule-based formant synthesis approaches, where basically, if you look at the spectrogram, you have somebody saying E, you can see what the formants are, you can work out the dominant frequencies, and you can just generate that spectrogram, or record that spectrogram and use it to synthesize. And you can actually make these physical models where you combine, you can make speech from a series of pipes, or even, there are examples of people with like electronic organs. If you play the right notes in sequence, then you can make it sound like it's speaking. Then people worked out how to do concatenative synthesis, and that's kind of the obvious way of doing speech synthesis that sort of everybody would think of if you were told to build a speech synthesis system is, I've got an example of what an E sounds like. I can just stick that next to the sound of a V. And if I've actually got a the in my database, every time I use the word the, I can use that example from the database. So that you can do that. You can just cut and paste chunks of audio once you've labeled them. But that was going to produce a very choppy signal. First of all, you're going to get clicks at the discontinuities. Very easy ways to work around that. But it's still going to sound not very natural because you're cutting and pasting these sounds from different parts of your database. Because it's very difficult to get a very representative database for the general case of speech synthesis. If you have a very limited grammar that you're going to synthesize, you can actually record a lot of the coverage of that database. So you record everything that you need somebody to say. If they only have to say 10 things, then just make a recording. You don't need to do speech synthesis. There's a sort of intermediate between recording and speech synthesis where you do phrase splicing. So like announcements like the speaking clock or platform announcements at a station, you can do by, you record, the next train goes to, and then you record all the place names that you might want to go to, and you record all the hours and all the minutes of the day, and you can just stick them together and generate a reasonably intelligible speech synthesis system with very little sophistication. But if you want it to sound really natural, then you have to do something a bit more complicated, and we'll come on to that in the next slide. And the final method is a model-based generative synthesis, where we build a model that is actually modeling the probability of the speech signal, and we're going to sample from that distribution or generate a maximum likelihood exemplar from that distribution. And over the last couple of years, there's been this shift from concatenative synthesis to generative synthesis. I mean, some of the earliest HMM speech synthesis was done back in the 90s, but only in the last few years has it really been challenging the concatenative synthesis in terms of quality. So I'm not really going to talk very much about concatenative synthesis, but this is a slide to just explain that. And basically, for all speech synthesis, we want to build a database that represents a good range of the kind of speech that we want to synthesize later. So we want lots of examples of each phone in particular. If we're going to model with diphones, which is typical in speech synthesis, then we want many examples of each diphone, so each transition from one phoneme to the next. And what you might do if you wanted to do concatenative speech synthesis is you do a forced alignment. So you build a very simple speech recognition model on your data. You do forced alignment to tell you where the boundaries are between the phones, or in fact, the boundaries between the diphones and the midpoints of the phones. And then you basically index all those diphones that you had in your database by their phone identities. So things, the K going into A sound is indexed according to those sounds. And then when you have a new utterance, you work out all the diphones that you need. You put it into a phonetic sequence of the phonemes. You see all the diphone transitions that you need. And then you take an example from your database. Now, that's where it starts getting complicated, is which example should you take? You know, some things you may only have recorded one. In fact, some, if you didn't record a very big database, you may not have any. Then you've got to work out how to back off to something else. But in general, you'll have many examples of each of these things. You've got to choose one. And basically, the standard thing to do is to find the minimal cost acoustic sequence by greedily choosing these units. So you start at the beginning, you choose your first diphone, which goes from silence to the first phoneme. You pick one which is the best, and you have a cost for choosing that. And then you go through the utterance, adding on the next diphone in turn, and you're basically trying to find the minimum overall cost, where a cost is how far away is this example from what I want? So, is this a good example of this diphone or a bad example? And how much does it mismatch with the previous diphone? So there's a unit cost and a join cost. And you basically want to minimize this globally, but typically people work left to right. And maybe there's a bit of a beam search to consider multiple hypotheses. And when you've got these bits of waveform that you've taken from your database, then you splice them together, and you don't just stick them end to end or do a blending, but you can actually look at the pitch periods which are the vocal tract opening and closing, and you can line those up and make them the same length before you do a blending. There's a thing called phased specific sensitive overlap and add, which is the technique for joining these things in a seamless way so that it sounds relatively good when you join them together. But you're paying a penalty in this join cost for ones that don't match very well, where you have to distort the signal to get them to overlap. And that can work very well. And even now, there are systems using neural networks to model these costs. So there are sort of hybrid systems which are using neural networks to choose the best units in a unit selection system. And basically, they work very well because you have real examples of real speech. So each of those units sounds very natural. And if you can do a good join, then the result can sound very natural. But to get really good, then you need to have a very big database. And that can be expensive both to collect and to store. So, for instance, getting a system that you can run on the phone, I think, at least until recently, the system on the phone was actually a concatenative system, but it means a very small database that you have to compress down. and you only have a few examples that you can afford to store. So the results aren't going to be as good as when you're sitting on a server with a huge disk array of many, many samples where you can pick the one with a really low cost. Parametric synthesis, where you have a model which you can make much smaller than the database, is very attractive for putting onto phones. So if you want to build a TTS system, you have to have some kind of database of audio, whatever kind of TTS system you're going to build, even just to learn the formats for the format-based systems, but particularly for unit selection and model-based generative TTS. And different to ASR, with ASR you want your database to match the conditions that you're going to recognize. With TTS, you generally want the highest quality possible. So you're going to do a studio recording where you're controlling the acoustic environment of the studio, you're preventing any background noise, because any background noise is just going to come straight through to your signal if you've got a unit selection system in particular. Consistent conditions, so that if you record half of your database in one studio and half of your database in another, just the room characteristics may sound different and give a jarring effect that reduces your quality. And typically, you want to choose a single voice. With ASR, we want to be invariant to the speaker in general. We want to recognize whoever speaks to the system. With TTS, you want to have a realistic sounding voice, so you typically get a single speaker and you record lots of audio from that one person. And to get a lot of speech, you typically have to get them to read the speech. Now, you can collect a database from existing recordings, like if we want to have a speech a synthesizer from a politician or an actor, we can go and transcribe things that they said in speeches and movies and things, but for a high quality voice, then we typically have read speech. But then it's going to sound like a read speech when we synthesize speech later. And that's a problem. So now we have a conversational agent. We don't want that to sound like read speech. So there's a lot of effort goes into getting professional voice talent who can speak in the way that you want them to speak, on demand. So you tell them, okay, we want a bright, conversational, engaging voice, and they audition lots of voice talent to see if they can do this, and can they do it consistently? Because to record 60 hours of speech is going to take months of work for that voice talent, because they can only work for, say, an hour a day and still give the high quality voice that you want for a professional TTS voice. So just a couple of examples. So one database that's freely available, I think, is this voice cloning toolkit. That was captured at Edinburgh University, and it's a kind of voice banking system where the people who are in the early stages of degenerative diseases, I think this is the intention, the population, they record these 400 sentences so that their voice can be reproduced later after they can no longer speak themselves. So they can train a speech synthesizer in their voice. So these are recorded at very high quality. There's a script prepared with very good phonetic diversity, and in particular there are some test sentences that elucidate your accent. So depending on which part of the country you're from, certain phonemes are going to be pronounced differently in certain words. There are sort of these test sentences that capture lots of those variations, so that they can train a voice for you specifically. And in this case, there's not very much data per person, but with these generative models, you can train an average voice and then adapt it on a small amount of data. And that's something that the hidden marker model, Gaussian mixed model systems have been very good at, is you train a generic model and then learn linear transformations in the feature spaces that map from the average voice into this specific voice and allow you to generalize from a very small amount of data to be able to synthesize a quality as though you captured a lot more data. Yeah?
People ever condition on different speakers to be able to increase the number that, say, one model can do? Is it beneficial?
Sorry?
Do people ever condition the model on, I guess, a particular speaker or stuff?
So you can do, I mean, particularly with neural networks, then you can do that. You can put in an embedding of the speaker ID, and actually have, there are things like eigenvoices as well, where you can sweep a parameter to generate different kinds of voices, like the first dimension that probably is going to drop out in any eigenrepresentation of speech is male versus female. You've got deeper voices versus higher pitched voices in particular. So there are those kind of representations where you can use that as a control, particularly, again, in the generative models. It's very difficult with the unit selection. You've basically got a bunch of units, and it's going to sound bad if you mix units from different people. But with generative models, then you can do these adaptation techniques. And they're fairly well developed for GMMs, but people are starting to do that for neural networks as well. So that's, there's 400 sentences per speaker there, but you've got 109 different speakers. Typically, you want to train a model on a single speaker. And for Google text-to-speech systems, then we typically have tens of hours of speech, up to 30, 50 hours for a single speaker to get a good range of data. But other systems, you can get a good speaker-specific system with just a few hours, say 5 hours, I think is quite common. And somebody was asking about getting linguistic features and so on for TTS, and Hager pointed me to the Edinburgh Merlin system that is on GitHub if you want to use an open source speech system. Something I didn't really talk about for ASR is how do we measure performance, but basically there the ultimate metric is usually word error rate. And that's basically an edit distance in words between the true transcript and the hypothesis that comes out of your speech recognition system. There are various ways that you might want to adjust that, like whether you get the pronunciation right, whether you get homophones right or not, and then you can look at the top 10 list and so on. But basically, it's the word error rate of the top one hypothesis is usually what we care about. For text-to-speech, it's very subjective. Basically, is this a good voice? Is in the ear of the beholder, really. One fundamental criterion is intelligibility. Although now we're at the point where we don't really have to worry about that so much for our voices. But in certain circumstances, it may be a criterion that you want to optimize for. So particularly if you're going to do station announcements, it can be very hard to hear a station announcement in the noise and reverberation of a station. You might want to sacrifice naturalness of the voice for intelligibility, so that people can actually tell what you're saying, and they don't really care if it really sounds like a natural voice. They want to know what it's saying as the fundamental thing. But for things like an assistant, then you can nearly always tell what they're saying. You don't really have to worry about the intelligibility so much, but you want it to be natural. Especially if I'm going to now have my assistant reading an audiobook to me. My tolerance for listening to an audiobook from a synthetic voice is pretty low if it's not very natural. That's why we pay actors to perform audiobooks and pay money to Audible to get these audiobooks. Because they do a performance, and we're just not there yet with text-to-speech systems, but we do want it to be as natural as possible for the uses that we do have. And this we typically measure by getting human subjects and getting them to rate the synthetic speech. So there are two main tests that are done. So the mean opinion score is you just listen to an utterance and you say how good it is. So on a scale 0 to 5, 5 is it's very natural. 0 is it's very artificial and very poor quality. Or you do A/B preference tests between two voices. So I have my old synthesizer and I tweak a parameter and I generate a new one. I synthesize a set of utterances with both of those things, and then I present both of them and say which do you prefer, A or B, and I randomize which order I present them in. And things like Amazon Mechanical Turk has made this much more feasible, rather than having to round up a lot of graduate students and forcing them to listen to these utterances. Now we can just put them on the web and just wait a few hours and it comes back. obviously Mechanical Turk isn't very controlled. You've got to maybe have a much bigger sample. But a lot of speech companies, now have dedicated units to have a set of trained Turkers that work for them in their dedicated system. But you can get on-demand, fairly high-quality A/B tests and mean opinion scores. But you do need to control for human factors. Like you want to compare two speech systems, but just to sort of ground people, you may keep interleaving natural speech in there so that you bring people back to what real speech should sound like, rather than getting distracted by the subtle differences between these two things. Yeah.
Has adversarial training become popular in speech generation?
Not very popular yet. I actually tried to do some of this about a year ago and wasn't successful. But there have been some recent papers just in the last few months on these generative adversarial networks for speech synthesis. Yeah.
How about loose alignments? It seems like there's a ton of available data if you don't need to have really tight alignment. Does that ever work very well? Or?
I think in general, then everybody does do the full, a tight alignment. But you can get that. How much you should trust it. Is there an absolute point where I make this transition from this thing to another thing but is it's not a real exact time. But I think a speech recognition system can be very good at working out where those boundaries are in some maximum likelihood sense. And these speech recognition systems, like if you've got a single voice, you're training a dedicated speaker-specific speech recognition system. So it can actually be fairly simple, like a Gaussian mixture model with relatively few components, because you're working on clean speech from a single speaker under these very constrained speaking conditions. It can be pretty simple. On that Edinburgh database, where you've got 109 speakers, then I'm not so sure how good that is then. Do they train a speaker-specific segmentation model? I'm not really sure. There are some kind of objective measures that you can use instead of going to people and asking them. And I just know a couple. So there are signal processing measures that you can calculate based on the signal for speech quality, perceptual signal speech quality. And then there's some work at Google being done on basically trying to predict the mean opinion score based on the signal. And that can actually do very well in some circumstances. So you can get a preliminary score, but ultimately the answer comes down to doing these human tests. And there's a competition, I think it's annually, called the Blizzard Challenge, where they different speech synthesis companies and academic synthesis systems compete to synthesize under certain conditions and from certain databases to get the best quality, and they use these human-based measures, and these different systems get rated. I think it's annually in the Blizzard Challenge. So now I'm going to talk about a probabilistic formulation for text-to-speech. And these slides Hager put together a very good sort of formal overview of different ways of doing speech synthesis. And basically, I've got these random variables. So I've got a data set of speech waveforms. So X, calligraphic X, is my big database that I collected. I've got a set of transcriptions of those, the text version. And now I've been given a new text, little w, and I want to generate a synthesized speech signal, little x. So I've observed the first three, and now I want to generate x. So one way of formulating this is I want to be able to model the posterior distribution of x given my databases and my input text. If I can model that distribution, then I can sample from the posterior to generate examples of the acoustics that match the text that I was given. And we know that this is a distribution. Every time I say the same phrase over and over again, I'm going to give you a different waveform So it is a distribution that we really want to model, not a specific, there is no definitive waveform for a given text. Although nearly all speech synthesis systems will give you exactly the same waveform if you ask them to synthesize the same text. They aren't doing this sampling, they're just picking a particular waveform, usually. So one way of solving this problem is to introduce these auxiliary variables, which is basically the speech representation. So in this case, I've got my acoustic features, my acoustic data, the waveform. I'm going to represent that with some acoustic features. So those are things like my FFT, my Kepstor coefficients, and so on. I'm going to go from the text to some linguistic features, and those are going to be things like phonemes in context and so on. And I'm also going to put a model in here, which is going to model the acoustic features from a given set of linguistic features. And if I factor my model like this, then I can come up with this formula for the probability distribution of an observed acoustic realization given my text and my data sets. There's this great big integral, where I'm integrating over all these possible representations and all possible models, and I want to come up with this Bayesian formula for the distribution of the realized waveforms. So this is obviously impractical to actually do this whole thing, but what we can do is we can do these point estimates rather than integrating over all possible representations and all possible models. I can come up with a particular representation, and in some cases I'm just going to choose this. So I'm going to say, okay, I'm going to use Kepstor coefficients, and in some cases I can train my model to produce a maximum a posteriori estimate. So now I can do an argmax instead of this integral. And in particular, I'm factoring into predicting the acoustic features O, and then from the acoustic features, I'm going to generate a waveform. So we can break it down like this. So in the first case, we're extracting the acoustic features. So I've separated it into lots of separate problems. I'm not doing an end-to-end optimization of the overall probability that I would like to optimize, but I'm going to separate it into a separate set of transformations where I'm either going to optimize them or I'm just going to fix them because I don't know how to optimize them. So in the first case, I'm going to extract some acoustic features, and typically that's done by hand designing. We pick one set. So from my acoustic representation, I choose a set of features, O. I can extract linguistic features, and again, I'm given a text, and I do all this hand-coded rule-based stuff to generate a set of linguistic features, typically. So I map it into the phonetic domain using some rules, possibly a neural network to tell me which pronunciation to use in some cases, and so on. And then I'm going to train a model to map between to find the probability distribution of the observations given the linguistic representation and the acoustic representation. I'm going to use my linguistic mapping to generate the linguistic features for my particular text to be synthesized, and then use my model and those linguistic features to choose an acoustic representation. And then finally, I'm going to synthesize the waveform, going from the acoustic representation to an actual waveform. So we've got these separate stages: generating acoustic features, linguistic features, and mapping into the acoustic features. Now the linguistic features, again, most of this has been sort of hand-designed over the years. At a higher level, we actually have the document. As I say, synthesizing an audiobook is different to synthesizing a single piece of text. We need to know the full context, but typically, that piece isn't very well understood or isn't modeled, and we generally look at individual utterances. So we take a sentence and we just model that out of its context, usually. And for things like a conversational agent, then that may be, you only have one sentence to synthesize at a time, but there is a lot of context about how you came to be uttering that sentence, even if it's not part of a bigger text. So we have sentence level features. So we have things like the total length of the sentence, how many words there are. We can break it down into phrases and look at the intonation of each of those parts. Do we have clauses? Do we have a question? And so on. And then looking at the word level, we have the part of speech. We have the grammatical function of those words, which words they are, which, for a text representation, which conceptual word is that representing, which might affect its pronunciation. Then we can look at the syllable level, and then finally the phonetic level. Mapping using these typically learned rules or some kind of model, a probabilistic model, to work out what the pronunciation for this individual word is. So we're going to try and represent some form of all these aspects in the linguistic representation. The most relevant ones are the ones near the bottom. If you don't get those right, then it's going to sound worse. But increasingly, we want to model these higher level things to make it sound more natural and more appropriate to the context. But we're at the very early days. We would just have one example of each phoneme, and we'd stick them all together, and we only have the lowest level. Now we're sort of working up this hierarchy to get more naturalness. And it's going to be very language dependent. All of these things are going to be different in different languages. Some things, there's relatively little information in some of these levels. Like the pronunciation of words in English is very complicated, but not in Italian. And this is all in this discrete NLP text-based domain. Something else that we're not going to talk about very much later, but is an aspect of the phonetic modeling, is if we're going to represent speech with acoustic features, which we say we capture as some kind of spectral feature. For synthesis, it's very often on every 5 milliseconds. They're on longer windows, like 10 millisecond windows, but every 5 milliseconds. Then we need to know how many frames a particular sound is going to last. And this could be modeled jointly with the rest of the acoustic features, but typically it's now done separately. So you have a separate duration model. And again, this is something that maybe you don't need to put as much effort into as, say, the trajectory. For a given speaker, their speaking rate, especially in a controlled database, may be very constant. So all the R phones may always last a very similar duration. And you don't need to model the duration very much. You just take the mean duration from your database. But you can put more modeling effort into this and say, have a feed-forward neural network to tell you, given these linguistic features, how long do I think this phoneme is going to last? And it will tell you, make this one 7 frames, make the next example of this phoneme 8 frames, and or it will give you a distribution, and you can sample from that distribution. But then you need to be sampling in a consistent manner. You can't sample independently from every phoneme, because that's probably going to give you different speaking rates, which are going to change. But we do need to have some kind of duration information for most of the modeling that we're going to see later. So one way of modeling speech is this source filter representation. So the idea is that speech sounds either modeled with a pulse train or white noise as the fundamental source, and then we can modulate that with a set of filters, so we have the vocal tracts opening and shutting, generating voiced sounds, which are modulated by the vocal tract, or say fricatives like the f and s sound, which are more like white noise, and then we can still put a filter on those to change the spectral characteristics of those to get different fricatives. So speech is often modeled as this source filter model where we pick a source, depending on the type of sound, so basically vowels versus consonants, pretty much. And we say the fundamental frequency, we have to model the frequency of that pulse train. And then we choose a set of filters that model the vocal tract. So if we want to synthesize speech, we can go from left to right. But if we're going to model this, then we actually need to take a waveform and convert it into these features. So what we typically do is we're going to estimate we'll take the FFT of the signal and compute the Kepstrom, like the Mel frequency Kepstrom coefficients that we looked at yesterday. Again, we want a low-dimensional representation for the traditional models like the HMMs and Gaussian mixture models to be able to handle the data because of the cursive dimensionality. And what we typically do is we're going to learn the mapping from the linguistic features into the acoustic representation. And then we have a separate model that does this mapping from the acoustic features to the actual acoustic realization. And that piece is called a vocoder from a voice encoder decoder, which those were developed as compression techniques to take in a voice, compress it down to a low bit rate, and then resynthesize a voice so going from acoustic signal to acoustic signal through a low-dimensional bottleneck. And again, these were hand-designed typically. And these use these kind of representation. So we've got a voicing. Are we switching between the pulse train or the white noise as our source? And then a spectral envelope, which we can represent as a Kepstrom. And if we are using the voiced component, then we also need to give a frequency. So we can compute these parameters for a signal, and then we can also, given those, we can synthesize a signal. And those vocoders themselves have got better. There was some recent work by Google where that they were improving the vocoder, and you can do a mean opinion score of just vocoded speech. So you're not synthesizing the speech. You just take a real acoustic signal, you encode it to these parameters, and then you reconstruct the signal. Basically, what is the loss in that? And you're getting MOS scores, I think, around 4.5 for that. So there's some loss in naturalness. I think natural speech doesn't get 5. In practice, it gets, say 4.6, 4.7. I'm not sure of the exact numbers. There is some loss in mean opinion score. People definitely can tell that speech is being vocoded, but it is quite a rich representation that allows you to get a pretty good quality score. Whereas the text-to-speech systems have been going from 3.5 MOS score, now they're getting up above 4 MOS score. So they're now closing the gap with just the pure vocoded speech. So if we want to train, the traditional system, we built rules for the modeling was done with rules. So we would use, the model would basically be mapping from linguistic features to the acoustic features with a set of rules in the original system. Now, suppose we want to try training a hidden Markov model was the sort of next stage. That was first done in the early 90s to learn what features are generated for each, for a set of text features. So we're going to replace the rules by this generative HMM. So a hidden Markov model, we've got this finite state automaton. Basically, for text-to-speech, we're going to have these left to right models. We don't have this branching system with, like we have for ASR, where we don't know what is being said. For speech synthesis, we're going to have a left to right model. We know the sequence of states that we have to go through. But we're going to model the emission distributions of each of those states. So typically, the states are going to correspond to these phonetic units. So maybe we have diphones, and maybe we split them into beginning, middle, and end. So we have a linguistic unit, L1 here, with 3 states. And in each state, we're going to emit some number of acoustic vectors. And that's going to be determined by our duration model, which, as I said, maybe we're going to model that separately, not as part of the HMM directly. So what we can do is we can do these forced alignments with an ASR-like system and work out which state each of our sample acoustic vectors belongs to, and we can train an HMM. So for each of these states, we can train a mixture of Gaussian's distribution for all the vectors that were associated with this state when we did forced alignments. What is the distribution of those? And we can train multiple components, means and variances in our Kepstrel features, and use those again at synthesis time by, for instance, we can just pick the mean of those distributions, or the mode, the peak value of each distribution as a representation of what we would expect it to sound like when we're in this state. And that produces a sort of a crude version of speech synthesis. It's very muffled, it's very smooth. You've averaged out lots of things. You took this big distribution and you picked one value that was always the same if you pick the mean. Sampling from those, I think, doesn't work very well because there's no consistent way of sampling. So we have these piecewise constant distributions that if we've trained these HMMs, we get a good estimate of the distribution. Sampling just randomly from those distributions without knowing how to condition them better than just the pure HMM isn't very good. But we can pick the mean and use that mean to generate speech. And it becomes intelligible, but as I say, it becomes very smooth, very muffled. You've averaged out lots and lots of examples into this one thing. You can get away from the piecewise constancy that every time I'm in a state, I only emit the peak by plotting a trajectory through those Gaussians. So you basically pay a penalty for moving away from the mean, according to the variance of that distribution. But you also want your trajectory in acoustic space to be smooth. So there were some techniques. I think Hager, he might have done his thesis work on this, sort of global variance optimization, where you want to optimize the smoothness of your trajectory through space while staying as close to the means that you think you should be emitting from these distributions. And that gives an improvement over the simple thing of just emitting a vector close to the mean at each stage. But another drawback with these HMM, GMM based systems was it's very hard to model high dimensional features. If you have high dimensions, you can't train a good Gaussian model because you don't have the parameters. You don't have enough data to train those parameters. And as we saw with ASR, if you use an HMM system, you can parallelize the training of these distributions very well, but you're only using the data to train the class that it's assigned to. And you don't get the generalization effect that we'll get with neural networks, where an example helps us train lots of the parameters, or all the parameters of the neural network, so it can help modeling. Any particular feature vector is going to help us modeling all speech rather than only the speech of the category that it was labeled with. But there was a lot of work on HMM-based synthesis. As I said, it started in the 90s, became popular again in about a decade ago, I think, as it became, it was becoming better, and people liked the flexibility that you had with HMM-based synthesis compared to unit selection. And you could do all these other things like adaptation, training multi-speaker models, do these eigen voices, and so on. So there has been a lot of work in HMM-based synthesis. But then, deep learning came along, and we decided to try doing some of this modeling with neural networks. I'll skip this. And we tried this. I mean, some people had actually tried something very similar in the 90s. Another student of my PhD supervisor did some neural network-based synthesis. But basically, the idea behind neural network-based synthesis is we replace the Gaussian distributions and the decision trees that we use to model the probability distributions, and we try to do that with a neural network. So we take a linguistic feature representation. It says this frame is going to represent this phone in this context of it's preceded by that phone, it's followed by that phone, it's in this particular word, perhaps. You know, we might have a particular pronunciation of that phone within a particular word, and you know, all the other linguistic features that we have. That it's it's near the beginning of a sentence. The sentence is actually a question. This is an adjective rather than the verb form or something like that. We feed in all those linguistic features as features to the neural network, and we try to predict the acoustic features as the output. So we just started with a simple fully connected feed-forward neural network where we fed in a bunch of features, mostly one-hot vectors, a concatenation of one-hot vectors of which phone is this, which was the previous phone, which was the next phone, and then trained it to produce a set of acoustic features that we extracted with signal processing on the data. And this worked pretty well compared to an HMM. One of the advantages of this is it's easy to make it not piecewise constant, in that you can put in a timing signal to say this is the third frame that you're going to be in this state. The linguistic features only change when you change from one state to the next. But we may emit multiple frames from a given state. With the HMM, that wasn't being modeled. But with a neural network, it's very easy just to add another feature, and we can get a smoother trajectory now rather than these piecewise constant distributions. And in this case, we're just regressing to doing a least squares fit to the acoustic features. We normalized them to be between 0 and 1, but just had a linear output in the output layer. The next obvious thing when we started doing recurrent neural networks for speech recognition was to apply that to TTS. So you now model it with a recurrent neural network, so you can get to build up context over time, see a long window of acoustic features. And again, that was found to improve the quality, and in fact, having a recurrent output layer was something that Hager found to improve the quality. So now, we were depending only on one linguistic feature, which possibly has some context, but is a limited window. Now we're depending on all the linguistic features back to the beginning of the utterance. And now with the neural network, we don't have these smooth stepwise statistics. We've got these more smoothly varying features, especially with this recurrent output layer on the RNN. Neural networks much better at handling high-dimensional features. Like we could start modeling in raw spectra even. And we can have very high-dimensional linguistic features that may not have been used by the decision tree simply because of the data sparsity. That basically decision trees, you're partitioning your data. Now we're generalizing across all these features. If a feature isn't useful, then it won't be used. But we're feeding all those features in for every acoustic frame, and when all our parameters are being used for every exemplar, we can provide it with much higher dimensional features that can be used if they contain information. And again, this distributed representation means we don't have the data fragmentation problem. So we can throw more parameters at the problem because they're all being trained on all the exemplars. So nowadays, neural networks are pretty standard, and there have been lots of different variants on using neural networks for text-to-speech, including the generative adversarial networks. And it's what is used by Google systems. on phones now, I think, for the smaller systems, but for some languages also on the server. The server, we had much more storage. We could store very big databases for concatenative synthesis. But for some languages, then we get better performance now from LSTMs for synthesis. So now we're modeling more of the process in the neural network. But the goal is to get all the way from text to waveform. So, what are the newer things that they're sort of trying to push the boundaries, not just modeling this mapping from linguistic features to acoustic features? Can we expand the role of the neural network to make it more of an end-to-end system? So there's been some work on learning the linguistic features, and learning the acoustic features. So there's some work on auto-encoding the FFT spectra and using that representation that you've learned as the representation. Instead of choosing to use Kepstra, then we can learn some, again, low-dimensional representation, but this time we're learning it rather than hand choosing it. And then some work on trying to learn the linguistic features as well, which has been less positive. There's been some work where they're now starting to combine different pieces of this optimization. So learning the source filter model and the acoustic model optimization jointly. I'm less familiar with this work. And some work that Hager did with a visiting professor at Google in doing this joint learning is trying to, so we're predicting acoustic features here and using them in the source filter model to synthesize the waveform and then backpropagating gradients from the from the waveform that gets synthesized. So by making this a differentiable system, we can backpropagate gradients through more of the system and jointly learn this acoustic representation that we're using. And that has problems because they had to break it down into the voiced and unvoiced components. So it was complicated, but did yield some positive results. But the most exciting thing that's happened in the last couple of years for text-to-speech is WaveNet, which was work done at DeepMind in collaboration with the Google text-to-speech unit. And this is where we're now trying to synthesize in the raw waveform domain. So having the neural network output the acoustic samples, not outputting some acoustic features, which then get vocoded into a waveform, but actually trying to generate the waveform directly. So WaveNet builds on previous work, the Pixel RNN and Pixel CNN, which was actually modeling images. But by modeling images with an autoregressive model where basically given the previous pixels, what is the value of the next pixel going to be in an image as a generative model of an image. And we saw that we could apply this to text-to-speech. It's actually simpler because it's now a 1D signal instead of a 2D signal. So if we have a raw waveform, which is a set of samples, x1 through xn minus 1, we can model the probability distribution, probability of x given some model, as with the chain rule, as we did with language modeling, as the probability of each sample conditioned on all the previous samples. So this gives us a way of modeling the probability of the joint probability of the whole signal, but breaking it down into a product of conditional probabilities. And in WaveNet, this is done with the convolutional neural network. And it uses these three things coming together that enable this to work better than previous work. So there was the resurgence of interest in these dilated convolutions. So convolutions with where you don't just take neighboring samples, but you actually have take samples that are far apart and ignore the samples in between. Or they used to be called atrue convolutions, with basically with holes in the middle. And then a combination of residual networks, skip connections going from deep in the network to the output layer, and a gated convolution where you actually have a product of a sigmoid, a logistic, and a tanh nonlinearity. And then the other thing that had been one of the revelations about the pixel CNN was modeling these things that we think of as continuous variables as discrete categorical distributions with a softmax rather than a linear output. So, as we said before, if you're modeling waveforms, you've got a lot of time steps. With ASR, we typically run 100 hertz, text-to-speech at 200 hertz, but at in the raw waveform domain, then we're working at, say, 16 kilohertz. That's 16,000 time steps per second. To learn a 1 second dependency, we need a dependency of 16,000 samples. So that's too far to be captured by a normal RNN or LSTM. But with these dilated convolutions, it's very easy to get very long-range dependencies. So the dilated convolution works by typically having very small filters. So in this case, this example shows filters with just 2 inputs. But we stack up filters with successively larger gaps. So at the bottom level, the filter sees 2 adjacent samples. But at the next level, you skip a sample. So you see, you only have to multiply 2 numbers by their weights, but you look further back into time. You skip one and take one further back. And at the next level, you skip up to every 4th, and the next level to every 8th. So you get exponentially increasing fields of view so this final unit, in only 4 layers, we've gone to 16 time steps, I think. And then by stacking these layers over and over again, you can also increase the range further. And typically, the WaveNet is built from blocks of, say, 8 layers. So we're getting time windows of the order of 256, 512 samples from each layer. And then by stacking up the blocks, we get even further. So now it becomes pretty easy to model these long-range dependencies. These simple convolutions are actually seeing samples from many time steps ago. And with the autoregressive model, basically we're using causal convolutions. So if you see, we haven't got these, the sort of typical image filter is 3 wide. You look at the position below you and 1 left and 1 right. Now we're only looking to the left, and this is back in time. So at time step x n minus 1, so here time steps n minus 16 to n minus 1 are all being used, combined together, to make a prediction of the value at xn. So it's like language modeling. We're looking at predicting the next value of this time series given all the previous values. But these dilated convolutions allow us to model very long-range dependencies, which are going to be necessary for waveform modeling. The architecture was built from lots of these residual blocks, but with skip connections going forward to the output softmax, or to a layer, which then feeds into the output softmax. So you're getting, each of these blocks sees quite a long-range dependency. As we go higher and higher, you see further and further, but we still feed the features from the first block through to this layer close to the output layer. The other thing was this idea of using categorical distributions. So we normally think of waveforms as continuous variables. It's a sound pressure level that we're ultimately recording, or a voltage in a microphone. We do quantize them, but we quantize them quite finely. And we're using typically 16 bits per sample. That's not something we would naturally model as a categorical distribution. But we found with pixel CNN that modeling pixels was much more was more effective if we used a categorical distribution. Pixels are typically quantized to 256 possible values, because it allowed you to model a wide range of distributions. You lost the fact that value 3 was right next to value 4. The model didn't really have any concept of that. With a softmax, you've just got 2 different values, which there's no direct connection between them. They're independent things. They could mean completely different categories in a lot of cases. But with enough data, the model, it does learn that they're close, but it's not tied to modeling a particular kind of distribution. So typically a linear distribution, you're going to output values which are close to each other with similar inputs. We don't need to necessarily do that with a categorical distribution. We can model very complicated distributions rather than being tied to modeling things like mixtures of Gaussians. So it's very easy to have unimodal, multimodal, skewed distributions, or even, particularly for the pixel CNN, things with a delta function at a particular value. Like basically, if your image is saturated, you're going to have lots of pixels of value 255, and it's going to be just a delta function at 255. So this was applied to the WaveNet for acoustic signals. 16-bit linear is too big to handle easily. It's hard to get that generalization across different values. But we first tried using 8-bit waveforms. Now, if you just did linear sampling of a waveform at 8 bits, then you get quite a significant quality reduction. But there's a representation called mu law, where basically you do a non-linear transformation of the linear signal first, and then if you do 8-bit quantization, then the quality is much improved. So the first experiments we did were with 8-bit mu law encoded signals, and we just predicted this categorical distribution across these 256 8-bit values. Dan Jarofsky is long been an expert in the speech field, and as he says, now we're modeling speech synthesis just in the same way as language modeling. We're trying to predict the next sample from a categorical distribution given a lot of previous categorical values. This is another. So originally, the very first experiments with WaveNet were just modeling the waveform. Can we get a generative model of audio? And they work pretty well. We could get good compression rates or reconstruction probability. The probability of the waveforms from the model the models became the synthesized waveforms were highly likely. Now we wanted to do a conditional model, so we want to condition the output based on the linguistic features. So we take the linguistic features from the standard system, embed those with a neural network, and we feed them in to each of the residual blocks of the convolutional stack. Yeah.
One question about the autoregressive part. So I remember from the natural language processing, actually, I think for translation, we know that usually we'll have to hold text. I think they usually use bidirectional, where you sort of actually like you use the history before it came before and what came afterwards. Like in text to speech, will also usually have the whole text available before you start. Why don't you use
So for an autoregressive model, you're trying to generate the next sample only given the history. You don't know what's going to come next. But for the linguistic features, we do know that. So the basic WaveNet is only looking at the samples. It's just modeling audio. It's not conditional. When we want to do text-to-speech, then we're going to condition it. And the conditioning information, we do have all of that. But the autoregressive piece is still going sample by sample. We're generating the next sample conditioned on where we were previously. We don't know what the future samples are going to look like. We don't have to model what those are yet. We'll come to those in sequence. We did this decomposition with the chain rule, where the joint probability was only modeled correctly by doing the chain rule, where we condition the next sample on all the previous samples. So it has to be unidirectional for the autoregressive model. But the conditioning information, we can embed that with a bidirectional neural network. And I think traditionally or historically we did this with a feed-forward neural network, but that's something that I think we've switched. That you do have the entire linguistic information available at one time. You can embed that with a bidirectional neural network or a non-causal convolution. You could do that. So now we feed the linguistic information into every single block. Again, this is sort of, a lot of this is empirical of what was actually found to work well. And now we're conditioning the next sample not only on the previous sample so that it generates a consistent waveform that sounds like audio that we saw in our training set, but it also is conditioned on the linguistic features, so it should sound like the thing that we told it to be saying. So before we had these problems with the conventional generative models. So we had the stationary model with piecewise constant modeling. You know, even with a neural network, we were synthesizing for windows, say a 20 millisecond window with a 5 to 10 millisecond shift. We basically say we've got one set of parameters that is going to characterize the envelope of this signal for that duration. Now we're modeling at the sample level and changing every sample based on all the previous samples. So we don't have this stationary process anymore. We used to have this very simple Kestrel representation to vocode. Now we're modeling every single sample. So it can model much more complicated. And we're modeling them with these complex distributions because it's a categorical. We can model these much more interesting signals now. And without the sort of Gaussian assumption that we have with some of the HMMs and the behavior of the neural network. So I actually have some samples that I can try and play.
The avocado is a pear-shaped fruit with leathery skin, smooth edible flesh, and a large stone.
So this is the hidden Markov
The
model.
avocado is a pear-shaped fruit with leathery skin, smooth edible flesh, and a large stone.
So that sounds a lot more muffled than the concatenative.
The avocado is a pear-shaped fruit with leathery skin, smooth edible flesh, and a large stone.
So that sounds better than the HMM, but there are some sort of strange sounds in there that don't sound natural. It does sound smooth, but it doesn't sound like a real human voice. With concatenative, you tend to get these point-wise malfunctions where you end up choosing a bad join and you get something that sounds discontinuous. With the generative models, you get these smoother things that flow well, but they don't capture the sort of brightness of the voice.
The avocado is a pear-shaped fruit with leathery skin, smooth edible flesh, and a large stone.
So it's generative model again, but sounds much more natural and less muffled than the LSTM and the HMM. And it opens itself to a lot of extensions that we can model multiple languages together, multiple speakers together in a single model. The kinds of things that some of the generative models like HMMs and so on have been doing, it becomes much easier to do some of those things in an LSTM, in the WaveNet model. So we've done jointly modeling multiple languages, multiple people in a single model. And there were some experiments doing simple speech recognition using the waveform representation and showing that the WaveNet loss of trying to reconstruct the next sample helped in speech recognition, although that was on a very small database, the TIMIT database. So what's sort of next for text-to-speech? So basically, like with ASR and lots of other fields, we're trying to make it end-to-end. So we're trying to incorporate more and more of these pieces into the single system. So can we feed in text analysis? Ideally, we want to go from the original text directly to the waveform without all these separate pieced-together systems that we're using for the text analysis. And that's relatively easy to build a system that does that. You just feed in characters instead of all the phonetic information, And for some languages, that will work straight away. Again, these phonetic languages, it may be very simple. But it may be a case of finding the right model architecture and collecting the right kind of data, possibly with some auxiliary losses and things to try and model all of this well, rather than better than we can with these separate systems. One way of getting closer to the complete Bayesian formulation that we had at the very beginning is to model the distribution by training lots of models. So we can approximate this distribution of integrating over the different possible model parameters by training an ensemble of different models by randomizing either the data set or the initialization or changing parameters of the models themselves that we train. So overall, we've presented the speech synthesis as this Bayesian formulation and shown how we break down the problem into these pieces, and then how we can begin to start sticking some of those pieces together to get closer to an end-to-end system, going from rules in the first place to an HMM to a neural network, and finally getting to this direct waveform modeling. And now the generative models are much more natural, or are more natural than the concatenative. It's only with WaveNet that we've actually got better results in terms of MOS and AB results for the generative, for the synthesized speech than the concatenative speech for things like English. But with things like WaveNet, the generative models, they're far more flexible. Things like modeling multiple speakers, having these parameterizations of, I want to generate a new speaker, just having a dial that I can change to say, I want a deeper voice, I want a faster voice, and so on. Things that you had to design really carefully, specialist signal processing systems if you had a concatenative system. Now it becomes much easier to do just by labeling some data and feeding in those extra labels to a model. You can start doing these things. So we can feed in an embedding for the language, an embedding for the speaker, an embedding for the gender, these kind of things, and then now we can start controlling these and conditioning on them. But text-to-speech is just part of a bigger system in general. So we want to expand, to be even more end-to-end. We actually want to take into account other factors, not just here's a sentence, synthesize it. We can realize that there are things like the sentence, Andrew Sr. is giving the lecture today. If I just gave you that text, you could synthesize it, but if you knew the context, you might synthesize it differently. So if I said, who is giving the lecture today? You would say, Andrew Sr. is giving the lecture today. But if I said, when is Andrew Sr. giving the lecture? You would say, Andrew Sr. is giving the lecture today. You'd change the emphasis. And the basic speech synthesis system doesn't take that into account. Often we may have markup that allows us to specify that, that we hand code, oh, this is the question we're answering, we want to emphasize this part, and we can put emphasis on that by having labeling in our original data set. But really we would like to learn that end-to-end and have some context that we're feeding into the WaveNet that allows it to make that distinction and learn the different kinds of prosody, where to put the emphasis, and then for things like if we're going from text to resolve the homographs, so to say the word Houston is, if we're in New York and we're talking about Houston Street, then it should be pronounced that way, but if we're in Texas, then we're talking about Houston for the same spelling. Putting all of that, having that learned as part of the network, rather than having a set of hand-built rules in advance. Hager put this as, we wanted text-to-speech to be able to represent, to synthesize the speech for all the world's information after we've made it universally accessible and useful, which was Google's mission statement. Another thing that we might want to do is actually build in a model of the speaker so that we can actually optimize more closely the things that we care about, and not need to do these human tests. Can we say improve the information intelligibility by optimizing the information received through the signal, by modeling the listener as well as the speech synthesis process. And there's always been an interest in doing model synthesis by recognition and recognition by synthesis, where you combine a speech recognition system and a text-to-speech system all in one. And then, potentially, you can backpropagate through the whole thing and improve both ASR and TTS at the same time. So, I've come to the end of the lecture. I'd be happy to take any questions either now or in front afterwards. So, are there any questions? General questions? Okay, thank you.